Hello everyone, and welcome to today's chem lesson. Today we are going to talk more about Bohr's models and specifically look at how he determined that these electron shells were a thing that existed. Right, if we remember the difference between Rutherford's model, which just said the atom is mostly empty space, and then Bohr's model, which says the atom is mostly empty space, but he defined these electron shells, right? Bohr had to figure out where the electrons were in Rutherford's model. Because Rutherford just said, they're somewhere outside the nucleus. So what Bohr's experiment did was by inputting a bunch of energy into an atom and recording what happened as that energy was released, he discovered these shells. He put in a small amount of energy and a large amount of energy and everything in between, and no matter what energy he put in, he got one of four results back. And he thought, that's weird. That shouldn't be happening this way. Right? That's like if you went out onto the sidewalk and took a ball and threw it up into the air with 1% of your strength, 2% of your strength, 3% of your strength, all the way up to 100% of your strength, and recorded how long it took the ball to come back. Right? You would expect a slightly different time for every percentage. But if it only came back at half a second later, 1 second later, 3 seconds later, you would think, something is wrong here. Right? It shouldn't be taking the same amount of time to come back into my hand if I throw it with 90 and 100% of my strength. And so what he determined was that these electron shells must be limiting the options for electrons to move around in. Right? They must only be able to go to certain points, and that's why I'm only getting these certain results back. Right? He determined that electrons can be excited and given energy. This makes them jump up to a different shell, and then when they come back to their original shell, when they return to what we're going to call the ground state in a second, they release that energy back. And since some of the energy is used to jump, it doesn't come back 100%. Right? So we only get those specific packets of energy back. Right? Let's look at that in a little more detail. Right? Let's say I have something like fluorine. Fluorine has 9 electrons, so 2 in the first, 7 in the second, 0 in the third shell. At the end, we're going to also have 2, 7, and 0. But in between, for a split second, we are going to have 1 electron out of place. Right? And what's going to happen here, as this atom absorbs energy, the electron will jump up. Right? The atom will absorb some energy no matter how we give it to it, right? Electricity, heat, sound, friction, the atom will absorb some energy which will cause this electron to jump up. But that can't stay this way. It's supposed to be 270. So eventually, the electron will fall back down. And this is going to release energy. Specifically, it's going to release some light. And this jump and fall is going to happen over and over and over again in the fraction of a few seconds. When you see a firework and one of them is blue and one of them is green, this is what you're seeing. You're seeing this light. Of old-timey neon sign, right? Before they were made with, colored glass, those were these principles. Right? The type of gas you put in there really made a difference. And we have different words for these two states of electron configurations. The one we're used to, the one we learned about last time, is called a ground state. Right? That's the one that matches what's on the periodic table. This, in the middle here, with one electron out of place, that is our excited state. So it's always going to be one electron higher than it should be. That's going to define our excited state. And so this process of absorbing energy, electron jumping, electron falling, and then releasing energy, is a split-second process. This happens super quickly, and it happens over and over and over and over and over again. And we can actually look at this light that's released and use this light to identify what element we have. We could actually reverse this process and look at the light and say, okay, if I'm getting this color blue, it must be from this element. And the reason for this is that every transition, right, falling from the third to the second, falling from the fourth to the second, from the fifth to the second, each transition gives a slightly different amount of energy, gives a slightly different color. And so these transitions create a fingerprint for our atom. Right? They create this set of lines that we can look at and use to identify if I see these 4 wavelengths of light released, this must mean I have this element. We could link that back to the identity of the element. Because every one of the shells is in a slightly different place, right? There's a slight range to the shells based on how strongly the nucleus is pulling. We get this unique set of energy readouts depending on what element you have. And we can take that one step further and actually look at these emission spectra, right? Look at these lines that are given and use them to identify what's in a compound or what's in my mystery substance. If I look at a set of emission spectra lines, I know that these 6 lines together would represent element A. These 6 lines together would represent element B. These 4 lines represent element C. These 5 represent element D. If I have a mixture of multiple elements or an unknown, right, any type of unknown, I can look at the spectral lines that they make. I can look at the emission spectra for this unknown thing or for this mixture to determine what substances it could be made out of. In this case, which 2 elements are in my mixture? When we look at something like this, we want to identify what lines are in both the mixture and one of the elements. So here, this mixture is actually a mixture of element C and element B, because it has all of the lines from C and all of the lines from B. This is an all or nothing process. None of the lines from D show up, so D is not in this mixture. None of the lines from A show up, so A is not in this mixture. But let's say for a second that A has these 2 lines as well. Even though some of the lines from A show up, the rest of them aren't there. All of the lines from an element must show up in your mixture or unknown for it to be considered a part of your mixture or unknown. Right, so even by adding these lines, I could add all 4 of these lines to A here. That does not mean that I add A down here, because these lines are not found in my mixture. And this process was actually hugely impactful for helping to fill in some of the harder elements to find on the periodic table. A lot of the elements actually only exist in compound form in nature. And so scientists were finding this thing, this compound, and saying this must be an element, because they didn't have the tools yet to figure out if this unknown thing was a element or a compound. They would just assume it was an element because it was something new. And by comparing the emission spectra of their new element, they were able to see that actually these things that they've been calling new elements were mixtures of previously discovered elements. And that really helped clear up a lot of the confusion that was happening as the periodic table started to get filled in. Right? As we were looking for specific elements, this process really helped say this is a compound, this is an element, this is a new element. This is a form of an element that we haven't seen before, but it's not a new element. And making those distinctions for people who are trying to fill in this table. Emission spectra are still used today when we look at out into space. When we record the emission spectra of a passing comet, or we look for the emission spectra of other, celestial bodies, we're checking the emission spectrum and seeing, is that a iron meteor? Is that a carbon-based meteor? And using that to determine what we're going to do about it. Now, to wrap us up for today, I do have one multiple choice question. Which of these electron configurations represents an atom in the excited state? Here, the right answer is choice 4. We're looking for an excited state configuration. We're looking for one electron out of place. Right, one electron higher than it should be. We know that in the first shell we can hold 2 electrons. In the second we should be able to hold 8, 18, and then 32 for the last 4 shells. So here, choice 1, 2, 8 is filled, filled, partially filled. That's ground state. That's following what we know. 2, 8, 1, filled, filled, partially filled, also ground state. 2, 8, filled, filled, that is also ground state. But 2, 7, 1, filled, partially filled, that must be our excited state. Because it has 1 electron higher than it should be. It should be 2, 8, 0. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.